Hello, and welcome to this week's Microfile, which gives you a chance to see again some of the best items from the MicroLive series. This week, we take a look to the future. Throughout the series of MicroLive, we've heard of new research both in Britain and abroad. Research into new computer architecture, faster forms of memory, and in the first instance, an alternative for the cathode ray tube, which is that bulky flickering screen we've all become used to. Now, obviously, the prize will be great for the first flat screen, which can be run on a low voltage and be clearly visible from all angles. STC are confident that their labs at Harlow have the answer.
A new computer display screen is being developed here at the STL labs in Harlow, which has significant advantages over the liquid crystal display screens available on current commercial computers. This Data General computer has one of the largest flat screens available today, and it's not all that popular. It has several disadvantages. Firstly, you have to view it at a rather narrow angle. If you move your head, the image can completely disappear. The contrast isn't all that high, and if you switch off the machine, the information disappears. Here, on the other hand, is a working prototype of the new thin flat screen they've developed. It's almost as good as looking at printing on a sheet of paper. The contrast and definition are so good. I can actually view it from any angle, and there's no fall-off in definition whatsoever. Perhaps even more importantly, this little example was connected 3 years ago, and the image is still there and readable. This display requires no refresh. Let's look at how this actually works. We've made a model of the display here with these two sheets of glass, and these are parallel lines of electrically conducting material photographically deposited on the surface of each of the plates. The surface of the plates and the real thing don't have to be optically perfect at all, and so ordinary glass can be used. The real problem was to keep the glass just 11 microns apart. That's about a quarter of the thickness of a human hair. And the solution turned out to be quite simple. They used small pieces of glass fibre threads thrown at random across the surface. We've represented them here by these small pieces of glass tube. The two plates are laid on top of one another like this, and the space in between the two plates is filled with a thick, viscous liquid. Where the lines cross, just like that, that square is in fact 1 pixel. And we can see this on the real thing by looking at it through the microscope. And you can see the real pixels there, and a few bits of the glass fibre. The real secret of the screen lies in this bottle. This is a very particular fluid that's been developed in this lab with very particular properties. A few drops of this is all that's needed to fill a normal-sized screen. When the molecules are lying at random, the light is scattered. When a high frequency is applied across the liquid, the molecules line up and the light can pass through the pixel. When it's switched off, the molecule stares the R, and the image remains until a low frequency is passed, when once again the molecules are scattered. This is much simpler than normal liquid crystal displays, which require polarizing filters and an image that has to be constantly regenerated, or as it's known, refreshed. But one problem with this screen is that it needs 200 volts to flip the pixels from one state to the other. The big challenge here comes in providing circuitry that can cope with 200 volts and can connect all the edge connectors from the screen into the computer itself. We can see this on this screen here. On the top here we have 780 connections, down the side 400, giving a total of 1/3 pixels. Well, this makes this extremely expensive to produce, so they've produced a special chip, and you can see them here on this piece of film. When these chips are bonded to the surface, they'll transfer much of the circuitry to the screen itself, enormously reducing the number of external connections which are needed. Once the electronics are miniaturized in this way, the scientists here are confident this screen can be made cheaply, use hardly any power, and end up being very compact. In terms of patenting inventions, the labs here at STC have a good track record. For example, they claim that fibre optics communications were invented here. This is where specially treated glass is drawn out into a thin fibre for use in telecommunications. The glass filaments used in the new screen were a spin-off of this technology. But inventing something is one thing. Turning it into a commercial success is quite another. We seem to be good in Britain at innovating things and completely fail in marketing them.
Yeah.
Are we going to be able to market this successfully?
Yes, that of course is a very good question. Our view is that we have to manage the exploitation just as well as we manage the research that leads to it. We've got to work out what the current technology can do, where it has a unique position, and so therefore where the customers are going to buy. And that has to be something that's as well managed, if not better managed even, than the research activity that's led to this product.
Are you really convinced this is going to be successful?
Personally, yes. I think this is one of the things that we must make work for Britain, and is a great tribute to the researchers in this laboratory.
What all this means is that we could have a high-resolution, non-flickering, portable, easily read screen the size of a piece of paper, or even larger, and all those cumbersome monitors will become a thing of the past. And there are new applications. How about having an online display for your overhead projector? The resolution's excellent. It's in black and white. But the most exciting thing is that they hope to have a small colour version available for test within the next few months.
Well, storing large amounts of information became much more practical with the reliable magnetic disk. And if you use a standard 40-track floppy disk for your micro, then you can store 300 kilobytes of information, or the equivalent of 30 pages of a telephone directory on each disk. The most recent development, the laser disk, can hold up to 2 gigabytes. That's 2,000 million bytes, or 200 phone books. But Freff has been exploring the mud swamps of North America and has found something even more rapacious.
At the Mellon Institute in Pittsburgh, Pennsylvania, work is going on to develop new solid-state devices to store information. Although it's still in the research stage, IBM is now funding the project. Leading the team is Professor Robert Burge.
This is a memory storage device, but how much does it store?
This device will store up to 100 gigabytes of memory, which is approximately 100,000 times more than the average disk memory device can store. And it can store it on a very small piece, roughly 1 centimeter by 1 centimeter, which allows for very high densities as well as very high speeds of memory access.
It's not exactly ready for the home market yet, is it?
Unfortunately not. We probably have at least 5 more years of development work to do. And there are a number of problems with it right now. For example, it has to work at 77 degrees above absolute zero, which is at liquid nitrogen temperatures, and that's not easily obtained in the home. And furthermore, it requires very expensive lasers to operate, 2 lasers in fact, and each of these lasers and present technology costs about $100,000.
The system uses a naturally occurring protein molecule called bacteriorhodopsin. It's found in the salt marshes of San Francisco. The molecule can exist in 2 forms, and these 2 forms can be used to store the digital information. So let's call them 0 and 1. State 0 can be flipped into state 1 by absorbing light from a green laser beam, and a red laser beam converts state 1 back into state 0. The green laser pulses on and off as it sends a stream of digital bits to the chip. In this way, it writes on the surface of the chip by flipping some of the molecules from state 0 to state 1. Reading the information back is more complicated. The same laser is then used to read the bits, and the way it does it is this. It scans the surface. Where it finds state 1 molecules, the laser beam travels right through the rhodopsin unchanged. But when it comes across a state 0 molecule, it flips it to state 1. As a result, some energy is absorbed, and the change in brightness of the beam is measured by a sensor behind the chip. However, in being detected, the bit has also been destroyed. So it's now the job of the red laser to reset the type 1 molecules to type 0 so that the chip is returned to its original state. It's rather like the way that old core memory stores worked, only much, much faster.
Is it a fair thing to say that these technologies you're experimenting with here are the real future of electronics, not the semiconductor technologies we're all familiar with.
I believe in most cases it is, because these devices, because they're so small, can operate at speeds 10 to 100 times faster than semiconductors and in much smaller operating environments. And therefore, as computers become faster and faster, eventually we'll have to outgrow semiconductors and replace them with molecular devices because of their speed.
So, on 1 square centimetre of mud from the salt marshes of San Francisco, one day we may be able to store enough information to fill 10,000 phone books, more than enough to hold the name and telephone number of everyone on Earth.
Although fast and easily accessible memory will obviously aid computing speeds in the future, there is a limit to the speeds available from the current processors. FREF moves east to New York City and Columbia University.
This is the inside of a VAX 11750, one of the most popular mini-computers in the entire world. And while it looks terribly complicated, it's actually based on a very simple idea. A processor and some memory linked by a single data stream. That's a structure known as a von Neumann machine, and it's pretty much the way every computer in the world is built, including the micro you have at home. But they're not all like that. Meet a non-von Neumann machine, non-von 1, built here at Columbia University. It ran for the first time in January of 1985. Looks a lot simpler inside, and that's because it's based on a totally different type of computer architecture called parallel processing.
Parallel processing is an attempt to get round what's called the von Neumann bottleneck. Modern transistors, the calculating part of the computer, can perform quite complicated functions in a billionth of a second, but it could take 10 times longer for the result to be passed along the wires, even though it travels at half the speed of light. Of course, one answer is to make the wires shorter.
Well, there's one critical problem with that, and that is heat. These elements that we now use that get these superb switching speeds also tend to dissipate a tremendous amount of energy. And when you compound that by cramming them all into a tiny amount of space, you can wind up with so much heat generated that unless you're very clever about the way you design your refrigeration system to go along with the raw machine, you wind up heating up those chips to the point where they don't work anymore. It turns out that silicon has a fairly narrow operating range of temperatures, and very quickly you wind up with something too hot to be practical. So in fact, the latest supercomputers really are very small, very highly efficient refrigerators.
The non-von answer relies on the fact that the processors, the chips containing the transistors, are now the cheapest part of many computers.
The machine that we're building right now, the non-von supercomputer, has a very large number of processors, each of which in fact is comparable to a small personal computer of the sort you might have at home. One important difference is that we have a lot more of them, each of whom can get instructions from the outside and have a little bit of local memory to store, say, a data element at a time and then process it independent of what anyone else is doing.
This independent processing, or processing in parallel, means that a problem can be broken into a number of components, each of which is solved at the same time and therefore faster. But there are some fundamental problems with this approach.
Probably the single most important one is communication. How do we get a machine designed in such a way that these different processors can talk to each other all at the same time and effectively and coordinate their execution of all these different pieces of the problem? That's the single hardest problem.
Connecting even a few processors together so that they can all talk to each other soon becomes unmanageable. So in non-von, the processors are organized in several different ways.
One of the key structures is what we call a binary tree, which is something that starts out with one processor up at the top that has two children, as we call them. Each of those have two children, and so on down to the bottom.
At present, non-von has only 64 processors, each on a separate chip. But the most recent development here is to put 8 processors configured in a tree format on a single chip. And eventually, they hope to have up to 1 million processors in future machines.
It's very exciting. The raw figures we get are absolutely astounding in terms of the amount of computational bang that you get for the buck. I don't know if that's an English expression, but what you get in terms of cost performance. But on the other hand, the basic problem that people may have is that if they got used to programming in Fortran or in C or in Pascal or a language like that, they may find the kinds of techniques that we use to be very foreign.
The non-von uses a parallel version of the programming language Lisp, and some types of calculations can can be speeded up 100-fold.
Suppose we had a business and we were trying to raise the salary of everybody in the sales department by 10%, but not raising anybody else's salary. We would store each employee record in a separate processor, and then there would be a series of instructions, each of which would be executed simultaneously by all of the different processing elements, but on their own employee record. That might say something like this. You could start by saying, take a look inside your department field. If it's not equal to sales, then turn yourself off temporarily and don't listen to what I'm about to say. Then the next set of instructions would say, multiply your salary field by 1.1. And at the end of that set of instructions, all of the salesmen would have their raises. And then we send out another single instruction which says, now everybody wake up and start listening again. So that's a typical way that in a short fixed amount of time, all of those different processors have done something to their individual memory elements.
Non-VON is the culmination of 5 years' work here at Columbia University, but this is not the only place that parallel processing is being explored. In a number of schools around the country, alternative approaches are being experimented with, and more than one company is set to release an actual commercial parallel processing computer. The one thing that all the creators of these different approaches believe in common is that their machines are the machines of the future.
The non-VON approach to parallel processing uses a large number of small processors. By contrast, the Bristol-based firm of Inmos offers build-it-yourself parallel processing. You buy as many as you like and slot them together in parallel. But that does not mean wiring up 1 million chips, for the Inmos approach uses much more powerful 32-bit processors, so you might only need 5 or 10. The principle is the same, though, with each chip having its own processor, its own onboard memory, and communication links with another chip or the outside world. Mac spoke to Phil Atkins from Inmos, who writes the demonstration software.
Phil, I really like your butterflies here. What are they showing?
It's a very simple demonstration, actually, just showing a pair of transputer talking to each other. We've got one transputer generating the images on this screen, one transputer generating the images on this screen. It's not that simple, though. One of the transputer is generating a butterfly, which is flying between the screens, so that data is being transferred from one transputer to the other.
It's the blue one. There it goes. It's just switched over.
We're using about 1% of the transputer's total resource. It's simply a demonstration of concurrency communication.
Now, can you buy this transputer today?
You can indeed. You can buy this board, which will plug straight into your IBM PC. Here's the transputer, 2 megabytes of memory and interface logic to connect from the transputer to the IBM PC.
That's 2 megabytes of memory. How fast is it?
That's about 10 MIPS.
That's about 10 times faster than the ordinary IBM A2, which is the fastest IBM PC.
That's right. You can plug 5 of these into the AT, in fact, giving you 50 MIPS.
50 MIPS, I can't believe it. How much is really usable?
45, 46 is pretty good.
That's very impressive. How do you program it? What languages are you using?
Fortran, C, Pascal and Occam.
Occam. What is Occam?
That's the language we developed at Inmos to program multi-transputer systems.
Well, we used to Pascal, we used to C and Fortran. Why do we need another language, Occam?
Well, you can program a single transputer in C, Pascal, but bind the entire system together in Occam to create a multi-transputer environment.
Is it difficult to learn?
It's not difficult at all, in fact.
Good. Well, I'll come back to you later, Phil. We've also been joined by the marketing manager of Inmos. Welcome.
How you doing?
Tell me, Chris, how much is it going to cost?
The particular board that we've just seen there, Mac, sells for £2,900, but for you, £5,000.
Oh, that's a real bargain. What about the chip itself?
The chip at the moment is selling for £420, but we expected that price, as with all semiconductor devices, to fall to around £50 over the next couple of years.
So that seems to be a good reason why I shouldn't buy one for 2 years.
Only if you want your competitors to get ahead of you, Mac.
So I should buy one now and really get to know how to use it?
Absolutely.
Do I get a copy of Occam with it? Does that come free?
You buy the Occam at a slightly additional price, the compiler and that for the AT will come together.
And I suppose I've got to pay twice as much for the Occam as anybody else.
Indeed.
Thank you very much. Tell me, how do you envisage it being used? What's the market for
There
it?
are many applications for the transputer that we're being designed in today, right from supercomputers through CAD workstations down to process control applications. One particular application that it's being designed into at the moment is the fingerprint project, which is being developed for the Home Office. In that system, the system takes and codes somebody's fingerprint and generates a 1 kilobyte image of that fingerprint. This is then distributed onto an array of over 1,100 transputers.
So that the actual image of the fingerprint is put in the memory inside the transputer itself?
Each transputer has a copy of that, and then the database from the Winchester is passed past those transputers, and they search then for the match.
And how big is the database?
Well, the database roughly at the moment is building up. There are 3.5 million criminals in this country, all of which have, say, 10 fingers, depending on their crimes. Each finger is a kilobyte, so we have 35 gigabytes of data that have to be searched. The system they're using today is based on some mini-computers and takes roughly 20 days, or would do, to search for that database, which is clearly impractical. With the transputer-based system, they can bring that down to a couple of hours. And by increasing, again, the number of transputers, you can get that down further.
So criminals, watch out. Where else do you see it being used?
The transputer is also very good for graphics applications. You can take a graphics image and break it up into separate parts and give each one of those parts to one transputer. Many transputers can then generate one frame, and many other transputers can then generate multiple frames, giving you real-time animated graphics.
Some of the stuff we've been seeing in the past is one giant computer just doing one particular screen and then filming it and making it look continuous. You've brought some very nice illustrations of graphics along today. Let's go and have a look at them. Phil, what have you got here?
I've actually got a very powerful machine here, 22 transputers working together to generate these images.
Slow down a minute. 22 transputers, is that 220 million instructions per second?
That's right, this is very powerful.
So that's the equivalent to 2,200 IBM ATs.
Yeah, I can demonstrate that, in fact.
Just to do a picture?
Just to do a picture. It's actually a very complex picture. It's the Mandelbrot set, it's a fractal. It's very compute intensive to generate this. About 6 hours on an IBM AT, and watch this. Very few seconds.
Now, just to repaint that screen would take 6 hours on
At least 6
IBM.
hours, something like 30 hours on the BBC Micro. We're about 7,200 times as fast as a BBC Model B here.
And each one of these lines here is actually being generated, by an independent...
by a different transputer, and they're being combined on the graphics system.
And 22 of them all intercommunicating.
All
we can
working
actually
together.
see it operating on a BBC Micro to see something and compare the actual things. There it is. It's slightly
not moving,
different
is it?
colours. No, it isn't. Well, you can also cycle the colours on this, can't you?
I can, yeah, watch this.
Go on, go.
It's
doing a lot of
pretty.
calculations now. There it goes. Well, that's very, very pretty indeed. Thank you very much, Phil.
Well, those graphics make real-time animation seem much nearer. Of course, most computer animation is achieved by lengthy drawing of individual pictures, which are then transferred to a single frame of film or videotape, and then run at speed to achieve the effect of motion. So, to finish the programme, take another glimpse at the futuristic and expensive world of the computer artist, as seen at the 1985 Computer Animation Film Festival. Well, Micro Live runs from October to March with a topical weekly show that keeps you up to date with the new technology, its applications and its implications. See you there. Bye-bye.